Continuing with 1.3, dealing with real numbers and their properties. Sorry, is that it? Yeah, real numbers and the number line. You got that. So starting to work toward this, the actual concept of working with a number line. A lot of this first part's going to be vocab, and I'm going to kind of leave it up to you to copy this and also hear me out as to how we classify some of these numbers and where they end up on a number line. So as far as classifying, the reason that we want to classify numbers like this and why we want to give some of these numbers descriptions versus just is this a small number or a large number, negative or positive, is because if we take a look at the number line, there's a lot of space that gets opened up over time as you get older and older. So when you were in kindergarten, they introduced what they call the natural numbers, or what I like to call the counting numbers. Because when you're growing up, and I'll even zoom out for this, when you count in kindergarten, you're just thinking, all right, well, let's start with 1. And then you go to 2, and then to 3, then to 4. And you even count on your hands, because when you're in kindergarten, you like the visuals. And then eventually they build in the idea that there's 0, that there's a number that's nothing. And you can't really hold up nothing. I mean, when you're in kindergarten, chances are you just did this, or you just shrugged and you were hoping that recess and arts and crafts was around the corner. So this kind of shows higher learning, because the natural numbers are what you started out with, just counting with on your fingers, 1, 2, 3, 4, 5, only going in the positive direction, really. And then starting to bring in the idea of 0, which I think is interesting, because to teach a young one the idea of 0, that a number is nothing, that's really fascinating to me. So if you ever run into your elementary school teachers, give them a heads up and say thanks. Then they introduce the idea, most likely in middle school, that numbers can be negative, which is what they call integers. So natural numbers, these are what you count with in kindergarten. Whole numbers imply that it's pretty much just the same roster, natural numbers, but now 0 is an option. And then integers, where now it's all over the number line from left to right. All the negative numbers, all the way to negative infinity, zeros included in the middle, and then all the positive numbers from 1 through infinity. So make sure you take notes on this. If you want to pause the video, take a look at it, go for it. We also get the idea of rational numbers and irrational numbers, and a little bit more of a definition here with what a rational number can consist of. So we say that rationals, there are certain families under rational numbers. Integers definitely make that, because those are from negative infinity to positive infinity, including 0. And the clarification here is that we can also have any number that's written in the form of a over b. So as a fraction, this is considered rational. And the reason this is because they terminate, meaning they end at some point. So even though here we have a bunch of decimals listed, we have 0.5, 0.4, 0.75, 0.7, 0.625, 0.3 repeating. Notice we have a decimal that's repeating, 0.83 repeating, and 0.363636, and the dot 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 shows it keeps going. The reason that we can classify these as rational is because they terminate and they stop, and they are repeating. So if we can write a fraction format like this, and the decimal terminates, it stops, and it's repeating, or actually it's or. So if the decimal stops or it's repeating, it's considered rational. And chances are we could write it as a fraction. Sometimes this can be tricky, but it makes sense. Whereas irrational, this can be non-terminating and non-repeating numbers. So numbers like pi, if you dealt with this previously in middle school, you would know this is 3.14. But in reality, this keeps going on for a really long time. And what's interesting is that even if we check a calculator, this looks as if it's going to end maybe after here. But again, this only shows so many decimal places. So pi is one form of any rational number, but pretty much any decimal that's non-terminating, meaning it keeps going and it's not repeating. So even if we had a decimal like 1, 2, 4, 5, 7, let's put in 3, then 9, then 0, this is kind of going in 1, 2, 3, but then notice it skips. And let's assume that this keeps going. This would be considered irrational. So if you need to take notes on this, pause real quick, take a look at it. We eventually build the idea that if we have rational numbers and irrational numbers, this represents all real numbers. So all of the numbers on the number line. And if we zoom in closely, this also includes fractions from every whole number, an integer number, all the fractions in between. If we have those combined together, those are considered real numbers because they are on a number line. We just might assume where they are. For example, if the decimal is repeating or if the decimal is all over the place and there's no pattern. So let's take a look at this. This table here is going to give us a little bit more detail on some of these numbers. There we go, that looks better. So here we're just going to classify how some of these numbers work. So if we have 2/3, that's definitely in a fraction format. And if we take a look at the decimal, it's 0.66666 repeating. And let's assume that that keeps going. So since this is a decimal that keeps repeating, we can say that this is rational for sure. We can't quite say it's an integer because this has a decimal to it. We can't say a whole number because it's not a whole number. Can't say it's natural either. But this is considered real. So that's fair game to say. Even though it is going to continue with that 3, 3, 3, that's fine. With -3, where do you think that's going to lie? I'm thinking that since this is a number on the number line and it's negative, it would have to be an integer. Think about this strategically. We can call this kindergarten for natural numbers when you were counting. Maybe in 3rd or 5th grade you introduced the idea of whole numbers, but integers, I don't think you saw those until middle school. Maybe earlier, but I'm not too sure. It's been a long time. We could also say that this is a rational number because this does end. We can also say it's real. For 0, what do you think? It's definitely a whole number, definitely an integer. We could write this as a fraction, so let's say it's also rational. It's also a real number. Square root of 25, this is just a 5 in disguise, so we can write that in. We can say that this is on the number line, and we learned this in kindergarten, so it's definitely natural, definitely whole, definitely an integer, definitely rational, definitely real. 5, there's nothing here. So let's look at this one. We have 0.33333 repeating. It's not a whole number. We could write it as a fraction of 1/3, however, and it does terminate, so that's why we want to say that, or no, sorry, it does not terminate, but there is a pattern, so we say it's rational, and it's also real. 0.625, it's not natural, whole, or an integer. We can say it is rational, however. I'm pretty sure this is 5/8 in disguise. 0.625. Since this does terminate also, it is rational, and it's also real. So we'll see different ways to clarify numbers like this. If you have any questions on this section, again, please reach out. My email's seen here, ccortez@cohs.com. Please make sure you're reaching out with questions.